Alright, in this video, guys, we're going to learn how to make confidence intervals. Now, let's first kind of explain what a confidence interval is. Think about an interval. An interval says that you're not sure what the answer is, but it falls from here to there. So an interval would be something like, hey, I don't know what the answer is, but I guess it could go all the way from this value, to this value. So that's kind of what we're looking for. We're looking for a confidence interval. Now, we got to shift gears here from what we've been doing in the past. All the other problems we've been doing so far have been dealing with these sampling distributions where we know the true P. We were told the true percent of Americans that are illiterate was 20%, or we were told that there was 13% of people are left-handed. But you have to understand that the true proportion is something that we usually don't know. Why do we take samples? We asked you guys this in class the other day. Why would you take a sample of people? And what would you be interested in? Well, a lot of times we take a sample because we're interested in finding, say, the percent of people that are left-handed. Or we're interested in finding the percent of people that are illiterate. Or maybe somebody told us that the true percentage of people that were illiterate in America was 20%, but we think it's changed. We think it's gotten lower. We think it's gotten lower and less people are illiterate. So what we would do is we would take a sample to investigate that. That's why we would do something like that. We want to investigate. We want to learn, right? Well, one of the issue is what if there's something new out there that we don't know at all, a new proportion. For example, in the Caribbean Sea, there is coral reef, right? These beautiful coral reefs that kind of look like this, and they fan out and they're gorgeous, right? But the problem is they're slowly being infected with disease, and I'm interested in knowing what percentage of them are infected with this particular disease. So I have no idea what the true P is. In fact, I'm trying to find it. So that's kind of the idea of an interval, is we're trying to discover what the true proportion of something is. So to understand how to find a confidence interval, let's first take a look at what we know so far with a sampling distribution, okay? We know so far that a sampling distribution represents many, many samples. So we have the true P in the middle. And we know that if you take the average of many, many, many samples, you should get the truth, right? The true average. That makes sense. And we know that a standard deviation of a sampling distribution is based on your sample, right? So it's the square root of PQ divided by N based on your sample size. So we know that it's possible to go up +1 of those standard deviations, +2 of those standard deviations, or we can go down 1 of those standard deviations, or we can go down 2 of those standard deviations. And we haven't talked about it being rare, but you could go up 3 of those standard deviations, or down 2 of those standard deviations. So a sampling distribution, right? This is a sampling distribution, represents what many, many samples would look like. For example, let's just make it a nice, perfect 100 samples. So if there was 100 students, and all 100 students had to look at a sample of, whatever, size 50. So we had tons and tons of samples. Well, what a sampling distribution tells us is that between -1 and +1, standard deviations, falls 68% of the samples. So 68% of samples will be within 1 standard deviation of the true value, right? We also know that 95%, I'm running into my work here, 95% of those samples, or 95, right, 95 out of 100, if there's 100 samples, 95 of those 100 samples will have a value, have a p-hat, will have a proportion that falls from positive to -2 standard deviations from the truth, okay? But again, this is all assuming that we know the truth. This is assuming we know the truth is in the middle. So we say that, here is the true value, and we could go plus or minus 2 standard deviations, and a standard deviation is, again, our formula here, the square root of PQ divided by N. So 95% of our samples, 95% of all the different, we found 100 samples, right? So 95 out of those 100 samples will have a sample proportion that's within that range. But like I said, the problem is that, what if we don't know what this P is? What if we don't even know what the proportion is to begin with? We're actually trying to discover it. So we have to use this a little bit backwards. Now, so I want to clarify a couple of things. First off, We have, since day one, been talking about 95% of data is in between -2 and +2 standard deviations. That's a little bit of a lie. It's not exactly 2. It's really, really close to 2. So all this time I've been saying above 2 is weird, below -2 is weird. It's not quite 2 and -2. It's really close, but I want to clarify exactly what it is. Okay, so let me do that, and let me explain how I'm going to do that. If I want to determine what z-scores have 95% in between them. We've been used to it being -2 and +2 z-scores, but it's not quite that. So I want to teach you how to find the right value. That means that there's 5% left out, 2.5% on the bottom, and 2.5% on the top. So if I do an invert norm, which remember gives me z-scores of 0.025, I get a z-score of -1.96. And that means the top 2.5% would be at +1.96. So we've been using -2 and +2 this whole time, but to be honest, it's actually -1.96 and +1.96. We call these values, excuse me, knew that cough was going to come. We call these values z-stars. Okay, they're important. They're critical z-scores, and we've been used to -2 and +2, but we're going to actually go with 1.96 and -1.96. Okay, so now that we have that down, let's talk a little bit more about how to find these confidence intervals. Okay, now here's the deal. We have no idea what percentage of these coral reef are infected with this disease. So we take a sample, and all we have is our p-hat. That's all we have. We have our sample proportion. P-hat, remember, is our sample proportion. We have no idea what the truth is. This is all we got, our sample proportion. Okay. The only other thing we have is our sample size. We do have our sample size because, well, we know that we looked at 500 coral reefs or whatever. Okay. We do have our sample size. That's it. So we have to try to estimate the truth from that and nothing else. So the first thing is we create a normal model just like this one, but we center it around p-hat. We center it around our sample, not the truth. Because again, that's all we have. We don't have anything else to work with. So then we want to think about standard deviations above and below. Well, we know that our standard deviation formula is the standard deviation for our sample proportion is the square root of PQ divided by N. Now remember, this is right here. This is the true P and the true Q, which, oh crap, we don't know. All we know is our p-hat. So what we do is we use the same formula, but we use p-hat and q-hat. Okay? Now, I can't call this a standard deviation. I'm not allowed to call it a standard deviation because the standard deviation is using the true P and the true Q, which, once again, remember, I don't even know. So what we do is, instead of calling this a standard deviation, we call this a standard error. This is the standard error of our sample. And a standard error is exactly like a standard deviation. It's just using your p-hat and your q-hat instead because you don't even know what P and Q are. Because, again, we have no idea what the true proportion is. We're actually trying to find it. So that's why it's sorry. That's why it's called a standard error. Think of it as the closest we can get to standard deviation, but it is not quite right. So anyway, we can go up +1 standard errors, +2 standard errors, and we can go down 1 standard errors, and we can go down 2 standard errors as well. Okay, so now this creates a normal model that it's not for P, it's for my proportion. But what I can learn from this, okay, is that I know that if my p-hat is falling here in the middle, right, here's my p-hat, I know that the truth has to be near it somewhere, right? I mean, go back to the sampling distribution, right? 95% of samples are going to be within 2 standard deviations of the truth. So if I think of this the opposite way, I think of the true p-value has got to be probably within 2 standard deviations of my sample. So that's how we build a confidence interval. And a confidence interval is trying to find the true proportion. So what we do is we say that p-hat's in the middle, and we're going to add or subtract, because we're within, 2 standard deviations. Well, wait a minute, we just had that talk earlier. It's not exactly 2. The better number to use is 1.96. So we are within 1.96 standard, again, not standard deviations. We have to use standard errors of that sample proportion. So we know that, again, this is, let's use a different color here. We know that we're going to use negative 1.96. It's just a little bit more accurate. That's all, guys. It's close enough to 2. I get it. It's just a little bit more accurate. So we know that 95%. What am I doing? Here we go. Let's just make this fun. I was trying to draw a squiggly line, but it wasn't working. So 95% of many, many samples. So think about many, 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 many samples. Many, many, many samples. 95% of those samples should create an interval that catches the truth. Because I don't know what the true P is. I'm hoping it's not out here. I'm hoping it's not out there. I'm hoping the true P is not out here. That would be rare. I'm hoping that the true P falls somewhere in this range from 1.96 standard errors below to 1.96 standard errors above. So let's kind of write out a nice formula for that. So what we have here is to find a confidence interval, call them CIs, right? A confidence interval for the true P. This is for the true proportion, right? We want to find the true P. Well, what we do is we start off with our sample proportion. We plus or minus a 1.96 times the standard error of the sample proportion. Now, remember, why standard error and not standard deviation? Well, because we have no idea what P is, and we're using P hat and Q hat, which creates this thing called standard error, not standard deviation. Why 2? Why are we using 2? Why are we using 1.96? Because 1.96 is just more accurate, and it reflects the 95% that we're talking about. So this creates an interval, right? This creates an interval. So it creates from a low value to a high value, because again, you're going to take that P hat and you're going to add it, and then you're going to subtract it. So that puts P hat right smack dab in the middle. So you're going to get a low value and a high value. And this is an interval for where the true P is. Okay? So we hope that the true proportion is within that interval. And we say that we are 95% confident. We say that we're 95% confident that the true P lies in that interval. Now, what does 95% confident mean? First off, it does not mean probability. It's not that there's a 95% chance that it's in that interval. Not at all. What it means is that if you ran many, 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 many samples, you would have many, many, many different P hats. 95% of those P hats would create intervals that contain the true value. Okay, and let me attempt to draw that picture of what I'm trying to talk about here. So let's just say that the true value is right here, right smack down there. Now, if Mike does a sample, and his sample creates this interval, hey, what do you know? He caught the true value in it. Jane, she does a sample, and she creates this interval. Hey, she caught the true P. Tommy, he creates an interval, and there's his interval. Hey, he caught the true proportion. Let's see here. Little Jimmy, okay? Little Jimmy, he creates an interval, and his catches it. Oh, my goodness, we're all catching that true proportion, right? Then we got... I'm trying to think. We got Austin here, right? Austin, he creates an interval, and oh boy, he barely caught it, but P did fall in his interval. Then we got, what are some other names here? I'm drawing blanks on names. We got little Nicky here, okay? And Nick creates an interval, and there's his interval. He missed it. His interval did not contain the truth. Well, first off, Nick's not going to know that, but that's what 95% confident means. That 95% of these many, I can go on and do this all day, 95% of these intervals that are created from different samples would contain the true P. Basically, if we did 100 samples, 5 of them would not contain the true P, and 95% of them would contain the true P. Okay, so let's do an example with this so we could see what the true proportion is. So let's say that I'm trying to find the percent of these coral reefs that are infected. So I go out and I investigate 222 coral reefs. Okay? And I find out that of those coral reefs, 46 are infected. 46 of these coral reefs are infected with the disease. Now, that means my sample proportion was 46 out of 222. So 46 out of 222 is 0.2072. I'm going to use 4 decimals here for accuracy. So 20.72% of my coral reefs were infected. Now, that's not the true, right? I mean, the true proportion, the true percentage, I mean, I would have to find every coral reef in the entire world and find out how many of them are infected. I can't do that. But I can estimate the truth with my formula here. So the only other thing I need is a standard error of my sample. I can't call it a standard deviation because I don't know the true P and true Q. So I'm going to have to use my 0.2072, and the opposite of that would be 1 minus 0.2072, which is 0.7928. So times 0.7928, and divided by my sample size, which was fairly large, 222. So I got the square root of 0.2072 times 0.7928 divided by 222. And that gives me a standard error, of 0.0272. Now, I should be checking my conditions as well. I need to make sure this is a random sample. I need to make sure my sample is less than 10% of the population, and I need to make sure I have 10 successes and 10 failures, which obviously I did. I had 46 successes, and the remaining out of the 222 would be failures. So just make sure you do check those conditions, please. Okay? Now, I'm going through it kind of fast to make the video shorter. Anyway, now it's time for me to create my interval. So I'm going to start off with the p hat that I saw, and I'm going to plus or minus. Now, I want to be 95% confident. 95% confident, right? And we all know what that means. Hopefully you do. I just explained it earlier. So I'm going to use 1.96. And once again, where did I get that from? If I'm 95% confident, there's 2.5 on the bottom, 2.5 on the top. Invert norm 0.025 for that bottom 2.5%, and you get the 1.96. And I'm going to multiply that by my standard error of 0.0272. Now, I noticed that looks like it might have something to do with the p hat, but it doesn't. It was just pure coincidence. So anyway, let me calculate that. So 1.96 times 0.0272 is 0.0533. So I get 0.2072 plus or minus 0.0533. Now, just so you know, just want everybody to be aware, this back number right here has a really, whoa, sorry about that. What happened there? This back number right here has a really important name. This back number we call the margin of error. Margin of error. Now, you may have heard that term before. It just means we're admitting, hey, we only have our sample. It might not be right. It could be a little bit higher, it could be a little bit lower. That's the margin of error. So remember sure that you understand that back number, the 1.96 times your standard error, has an official name of the margin of error. And we'll talk more about that in the next video. But anyway, so I'm going to take my 0.2072. I'm going to subtract 0.0533 to get the bottom of my interval. The bottom of my interval is 0.1539. And the top of my interval would be the 0.2072 plus 0.0533. And I get 0.2605. So this tells me that I'm 95% confident that the true proportion of infected coral reef of the disease is anywhere from 15.39% to 26.05%. And you would need to write out that statement. You want to explain your interval. So I'll say that one more time. I'm 95% confident that the true proportion of infected coral reef is anywhere from 15.39% to 26.05%. So I'm only 95% confident, which obviously is pretty good. That just means that there is a chance that my interval does not contain the truth. That means that I would be one of the 5 out of 100 samples whose interval did not contain the truth. Please do not look at it as a probability, like there's a 95% chance that the truth is in there. It has nothing to do with probability. It's all about the fact that you're doing a sampling distribution, which represents many, many, many samples. And of those many, many, many samples, 95% of them would create an interval that contains the truth. I'm just crossing my fingers and I'm hoping that my interval is one of those that does contain the truth. Again, I have no idea what the true percentage of of infected coral reef are, but my sample shows, along with my margin of error, that it hopefully, with 95% confident, is in that range. So that's a quick little video over confidence intervals with proportions. There is a way to do confidence intervals with means, and we'll talk about that in class and over another video as well. All right, guys, so hope you have a good weekend, and we're going to do some practice problems with this stuff on Monday, or Tuesday. See you guys.